Okay, good morning to all. So, this is our sixth lecture session of the course Fluid Mechanics. In the previous lecture, we have started our discussion on a very important property of the fluid flow, which is typically called as viscosity. Okay, so if we just quickly revise whatever we studied, so viscosity we have defined nothing but a property which is a quantitative measure of the internal resistance of the fluid to its flow. Okay, and viscosity is having like different mechanism of its action for liquids and for gases. For liquids, it is because of the cohesive forces, and for gases, it is because of the intermolecular collisions. That is the reason we observed that when we increase the temperature, then viscosity of the liquids decreases and viscosity of the gases increases. Okay. On contrary, pressure is having very small effect on the viscosity of both liquids as well as gases. Okay. And with the help of viscosity, we have come up with very important law for defining the relationship in between the shear stress and the rate of shear strain, which that particular relationship is actually directly proportional to each other as per the definition of the fundamental definition of the fluid. But when that proportionality is converted into equality, there comes a coefficient mu, which is called as dynamic viscosity. Okay, and that particular dynamic viscosity, basically we are seeing that gives, if its value is constant, it means the relationship between stress and shear strain is linear, then we get nothing but a special type of fluid which is called as Newtonian fluid. Okay, any fluid which does not follow this relation tau equal to mu times del u by del y, particularly, or even in one dimensional situation I can write du by dy. So particularly if I consider that my dynamic viscosity is constant, now any fluid which will not follow this type of relation, that is called as a non-Newtonian fluid. Okay, now for studying the non-Newtonian fluids, we have seen that for studying the non-Newtonian fluids, we have seen that we are having different types of possibilities. Okay, so if I try to draw these possibilities over here, so you will be finding I can have this relationship in between shear stress tau and rate of shear strain, which can also be written in the form of velocity gradient du by dy. Okay, so if I see this particular curve, then what I will be having for Newtonian fluids, as I already told you in the previous lecture, that relationship is directly proportional and mu is constant. Okay, so it means I will be having a straight line, something like this. So this is nothing but for Newtonian fluid. Okay, so up to this point we have studied in detail. Now one important point, you are seeing that this line is nothing but passing through the origin. So the why it is passing through the origin means if we give infinitesimally small amount of shear stress, then also we will be having some rate of deformation, or we will be having some shear stress or velocity gradient in the fluid. Okay, so that is the fundamental definition of the fluid. That is why this line is actually passing through the origin. Now we may have one special type of fluid. So particularly if you see the examples we have seen in the last class as well, so air, water and other common oils such as glycerine, silicon oil, etc. are nothing but the examples of Newtonian fluids. Okay, but we are having certain other types of fluids for which this shear stress and rate of shear strain relationship is not linear actually. Okay, or in other words I can say that whatever the viscous term over here we are having, that is not constant, that changes when the shear strain, rate of shear strain, or I can say the velocity gradient of the fluid layer actually changes. Okay, so in these type of situations we can have different types of fluids. So one common fluid which you might have experienced is actually known as quicksand. Okay, so if you mix sand particles in water and make a thick mixture, so you will be finding sand is almost staying. If you see the layer of sand in some portions of the land, then you will be finding initially it is staying. Okay, if you put your feet over that, what you will be finding? When we are putting the feet, actually we are displacing it. Once we are displacing, it means some sort of rate of deformation or velocity gradient is developed inside that sand. Okay. So whenever the deformation is developed inside that, that sand actually becomes so thick that it completely holds our feet. Okay. So that is a type of fluid which is actually getting thickening when we are subjecting it to the shear or the velocity gradient. So this type of fluids are called as shear thickening fluids or dilated fluids. Okay. So what will be happening in case of shear thickening or dilated fluids? If you try to draw the stress strain relationship, you will be finding that it will be something like this. So whenever your rate of shear strain or velocity gradient is increasing, the amount of shear stress required to achieve some amount of rate of deformation is actually also increasing. So it means that if you see the in terms of linear relationship, you have seen that for air we were having very small slope, and for water there was some intermediate slope, and for oil there was very high slope. It means that whenever this instantaneous slope of the stress strain curve is increasing, it means actually our constant of proportionality is increasing. Is this one clear? So now if you want to measure instantaneous slope, so at this point your slope will be something like this. At this point your slope will be something like this. At this point your slope will be tangent to the curve, something like this. So it means as you are increasing the rate of deformation, with increasing the rate of deformation, your slope of the stress strain relationship is actually increasing. So if slope of the stress strain relationship is increasing, it means this coefficient of proportionality what we have, that is increasing over here. Okay. So when the coefficient of proportionality is increasing, we can say that thickening of the fluid is actually taking place. Okay. So this type of fluids are called as shear thickening fluids, or the other name is dilatants. Okay. So dilatants or shear thickening. Fine. Then we have other situation. So some of the fluids are, so example, just now I have given the example is quicksand. You can refer through your text and different sources for finding more examples. So one example I have quoted you. Now another type of fluid which, what will be happening, which will be thinning when we are actually, what we are doing, when we are subjecting it to the rate of shear strain or the velocity gradient. Okay. So one common example is paint. So if you see, if paint is inside a box, then it will be appearing very, very thick. But if you take some stick and start rotating it, initially it will be appearing very thick, but after certain amount of time you will be finding that it will be kind of start rotating almost with lesser effort. Okay. Similar is the thing. So whenever you just take your brush, paint brush, and you dip inside the container of the paint, then you will be finding it's very thick and it gets stick to the brush. Okay. But once you start rubbing the brush, it means what you are doing? You are giving high velocity gradient. Okay. You are, when you are actually rubbing it on the wall, then you are giving velocity gradient, or you are giving rate of shear deformation. So when you are giving that type of deformation, in that scenario what will be happening? It gets thin and layer of paint gets wetted on the wall. Okay. So this type of fluids are called as pseudoplastic or shear thin fluids. So how stress strain relationship will be here? So you will be finding that initially, means for the smaller rate of deformations, amount of shear stress required is more, but as we are moving ahead, that requirement of the shear stress is actually decreasing. Okay. So this type of fluid is called as pseudoplastic or shear thin fluids. Now there is one more type of fluid where what will be happening, where initially it will be behaving like a solid, okay, and once you have supplied some amount of shear stress which is enough to make it fluid, after that it will flow like a fluid. So that type of fluid is called as ideal Bingham plastic. So this is called as Bingham plastic fluid. Okay. So what will be happening in case of Bingham plastic? The example is, can you tell me any example? Toothpaste. Okay. So in case of toothpaste, if you see, initially it is behaving like a solid. Then we have to apply some amount of pressure on the tube of the toothpaste, but it not always comes out. So we have to apply some significant amount of initial push. Once it has overcome that initial push, so that is nothing but this is the yield limit for this fluid. Once we have reached this yield limit, after that it will flow like a fluid. So this is nothing but ideal Bingham plastic. So if after this initial stress, this is behaving like a straight relationship, then we call this as ideal Bingham plastic. Otherwise, simply we call, if it is following some sort of this type of relation which is shown by a dashed line, it means stress strain relationship is not linear after the yield stress, then we call it as simply plastic. Okay?
So before the threshold it acts like a solid.
Solid, yes. Because inherent property of the fluid is, if we give any small amount of shear stress, it should flow, but it is not flowing. So before that it is behaving like a solid.
Cornstarch. Cornstarch.
Yes, cornstarch.
But that happens.
Yes, yes. Cornstarch comes in one of these two categories. Which one you try to identify? Either shear thinning or shear. Okay. Okay, now what we have to do, so this is something which we have talked about this. Now so there are multiple stress strain relationships. So for Newtonian fluids, we have seen tau equal to mu times del u by del y. For defining the stress strain relationship between non-Newtonian fluids, there are multiple relations available. Okay, but what we have to do, so because this is not the subject of our particular course, so now for non-Newtonian fluids there are separate courses, but over here just I will try to give you one of the model which is very commonly used for depicting the behavior of shear thickening and shear thinning fluids, which is called as power law model. Okay, so in case of power law model, what we do basically, we represent that shear stress is nothing but equal to K times du by dy power n minus 1. Okay, so over here what we can do, if I want to write, so what I have done in power law model, I have written tau equal to K times du by dy n minus 1. Okay, now if I want to represent it in the form of previous relation whatever we have used for stress and strain, then how I can write, sorry, this will be du by dy n. Okay, so now if I want to write it in the form of previous relation which is identical to that of Newtonian fluid, so what I can do, I can write it tau equal to K times du by dy power n minus 1 into du by dy. Fine. So over here, if you see what was the relationship for Newtonian fluids, tau equal to mu times du by dy, where mu was nothing but our dynamic viscosity, which was having constant value for all the shear rates. Okay, so over here, this is my shear stress, this is rate of the shear strain or velocity gradient. So it means this entire quantity K into du by dy n minus 1 is something which is mimicking nothing but our viscosity. So this quantity is mimicking over here viscosity. Okay, so this particular quantity we call as nothing but the apparent viscosity of the fluid. Okay, so we have called this quantity, which is not exactly the identical to the viscosity, dynamic viscosity which we used in case of Newtonian fluids, but just similarly satisfying the stress strain relationship. Okay, so this is called as apparent viscosity of the fluid medium, and here we are having two coefficients. So K is called as flow behavior index and N is called as flow consistency index. So K and N are two different coefficients. One is called as flow behavior index and other is called as flow consistency index. Now, typically you will be finding in case of what is happening in case of shear thickening fluid. In case of shear thickening fluid, your value of apparent viscosity is increasing with the shear rate. Okay, so it means that if this value K del U by del Y has to increase, then for shear thickening fluids N has to be greater than, for shear thickening fluids N has to be greater than 1. Is this one clear? Okay, ultimately we are having K into del U by del Y N minus 1. Okay, so if N will be greater than 1, then whatever the quantity we are getting, that will be coming in multiplication. But for shear thinning fluids, because whenever shear rate is increasing or velocity gradient is increasing, then what is happening? Our viscosity of the fluid is decreasing. So for this situation N has to be less than 1. When N will be less than 1, then del U by del Y whole term will be becoming negative power and it will be divided, it will be dividing K. So which will be decreasing the overall apparent viscosity. So for shear thinning fluids, our N will be less than 1. Is this point clear? So for shear thickening fluids N is greater than 1 and for shear thinning fluids N is less than 1. And typically if you plot apparent viscosity as function of the shear rate, and here you are having say mu apparent, then for Newtonian fluid it is constant. Apparent viscosity increases for which type of fluid? Shear thickening, and it is decreasing for shear thinning. Okay, so this is how I can represent the apparent viscosity. Now there is one more categorization which is typically done in terms of relationship between shear stress and time. So based on that characterization, we call the fluids as rheopectic and thixotropic. So what we have to do is, I can plot a relationship in between time. So this side I have say time and this side I have tau. Okay, now with tau, if I have to maintain a constant shear rate, so in this situation I want to maintain constant du by dy with time. So with time I don't want that shear rate should change. Okay, so if I want to maintain constant shear rate with time, then for Newtonian fluids I will be finding that my tau will remain the same. Okay, but for there will be some fluids for which if I want to maintain the constant shear rate, my shear stress should increase with time. Okay, so I will be having curve something like this, where shear stress is actually increasing with time. So the fluids for which we have to increase the shear stress with time in order to maintain the constant rate of shear strain, these fluids are called as rheopectic fluids. Okay, and fluids for which in order to maintain the constant shear rate, if you have to decrease the shear stress with time, these fluids are called as exotropic. Okay. Okay, so if we have to maintain constant shear stress, constant rate of shear strain du by dy with time. So we don't want to change rate of shear strain with time. We want that fluid should go through this shear deformation at the constant rate. Then for some fluids, what we have to do, because these will get thickening with time. Okay, so for these fluids, what we have to do, we have to keep on increasing the shear stress with time in order to maintain the constant shear rate. So these are called as rheopectic fluids, and fluids for which will be actually with time, which will be thinning out. For these fluids, we have to decrease the shear stress with time. Okay, so over here you can see one important thing. Fluid is not changing viscosity with shear rate, because in all cases shear rate is maintained constant. Okay, but fluid is changing viscosity with time. So shear rate is constant. Whenever it is changing viscosity with shear rate, then we were having categorization as shear thickening and shear thinning. But in this scenario, what is happening? Shear rate is actually, rate of shear strain is constant. That is not changing. But with time, one fluid is getting thickened and one fluid with time is actually getting thin. So whenever the variation in apparent viscosity of the fluid happens with time, then we call fluids as rheopectic and thixotropic. So please make this point very clear. In case of shear thickening and shear thinning, changes in viscosities are due to the changes in shear rate. But in this case, shear rate is constant. So changes in viscosity are with time. Okay? Is this point clear?
So you give examples.
So what you can do, for examples, you can, lots of examples are given in your text and reference books. Okay, so try to refer to. Some of the common examples are shape memory alloys. So you can see some fluids which changes their shape whenever these are subjected to shear stress, but after some time, whenever you are removing the shear strain, they are once again coming back to their original shape. Okay, so many such examples you will be finding actually in your textbook. So for that, refer to the text. Okay. Now comes other type of fluid property. So almost we have seen the general categorization of different types of fluids, but this is just for your initial understanding. We will not be dealing with any of these types of fluids in detail in this particular course. Here we will be referring to only the Newtonian fluids. Okay, so now there is another variant of the dynamic viscosity, which is typically called as kinematic viscosity. Okay, so can you tell me what is kinematic viscosity? It is given by symbol nu, and it is nothing but the ratio of dynamic viscosity by density. Okay, so ratio of dynamic viscosity by density is something which is called as kinematic viscosity. Kinematic viscosity is very important whenever we study the fluid flow and heat transfer problems. Okay, typically whenever we study the relative competition between the momentum transfer and the heat transfer, then comes its importance. Okay, so you can see that kinematic viscosity, because it is involving the dynamic viscosity, so ultimately it is also representative of internal resistance of the fluid flow. But the difference is, here we have divided it with the density. So as we have divided it with the density, it is not depending upon the content or extent of the fluid. Okay, so over here if you dimensionally see its unit, you will be getting in SI units as meter square per second. Okay, so meter square per second is its unit in SI units, and typically the popular unit of kinematic viscosity is nothing but Stoke, and 1 Stoke will be equal to 1 Stoke is how much? 1 Stoke is 1 centimeter square per second. Okay, so if we write it in centimeter squares per second, that becomes equal to nothing but 1 Stoke. So basically the more importance of kinematic viscosity comes whenever we want to study that how fast the momentum is actually transferring between the subsequent layers of the fluid. Okay, so unlike dynamic viscosity, in case of dynamic viscosity, we studied that for both liquids and gases, it does not changes significantly with pressure. Okay, on contrary, if you see dynamic viscosity is involving rho over here. Sorry, this kinematic viscosity is involving rho over here in the denominator, and rho is a strong function of pressure. So it means that when there are changes in the pressure, then kinematic viscosity of the fluid will also be changing significantly. Okay, because there will be significant changes in the density of the fluid. Okay, now apart from density, another important property of the fluid medium is which is called as surface tension. Okay, so surface tension is very important property of the fluid medium. It is having many practical implications in whatever the phenomenon which we observe in nature. Okay, so can you tell me what do you understand by surface tension? Anyone is having any idea about surface tension? Surface is trying to contact itself. Okay, minimize the surface area. Yes. Anything else? Surface tension is the property, this point is correct, that surface tension is the property of the fluids because of which only fluids tries to minimize the surface area. Okay, so as fluids minimize the surface area, that is the reason that if you see the small entities of the fluids like drops, bubbles, these are typically having the spherical shape, because spherical shape is the shape for a given volume having least surface area. Okay, so let's try to fundamentally see the how surface tension originates at the surface and what are its different interpretations. Okay, so typically if I take a container, as we have seen that if I pour a liquid inside this, okay, so if I pour a liquid inside this, I will be having some free surface over here. Okay, and inside this, say I have liquid. Now this liquid, you can take any liquid, say for the time being I am considering it as water. Okay, now what will be happening, I will be having number of molecules over here. So if I take any molecule in the core of the liquid, this molecule will be feeling equal amount of attractions from all the directions. Why? Because it is having all like molecules around it. Okay. On contrary, if I consider a molecule over here, so here at this point what will be happening, in this side it is having both sides water, so it will be facing equal interaction. Bottom also there is water, here also it will be facing equal interaction, but from the top we have nothing but air molecule. So here we are having air. So now it depends upon that typically at molecular level we are having two types of forces. One are cohesive forces, other is adhesive force. So So in terms of cohesive forces, we say that the attractive or intermolecular forces shared by like molecules are nothing but called as the cohesive forces. On contrary, the forces between two different types of molecules are referred to as the adhesive forces. Okay, so I can say that for water, adhesive forces are very less in comparison to the cohesive forces between the water molecules. Okay, so because of this, from this top portion, this particular molecule will not experience any attraction forces. Okay, on contrary, from bottom side and its sideways, it is experiencing in this half sphere, it is experiencing the attractive forces. Okay, if you see other molecule which is at the center, it is experiencing almost same forces from all the directions. Okay, so you can see that the molecule which is experiencing equal forces in all the directions, it is kind of in nothing but stable or balanced state. Okay, so I can say it is in the happy state. But on contrary, this molecule which is actually having some net force acting in inward direction. Okay, because from the top side, molecules are not attracting it, so it is having a net force which is acting in downward direction here. So because of this net force, what will be happening, it will try to create some compression effect on the molecule which is just beneath it. Okay, so as it will try to compress it, the molecule which is in the beneath, that will try to create some repulsive force and will try to maintain it at its location. Is this point clear? Whatever I am trying to say, is it clear? So what I am saying is, this molecule, because it is having less attraction from the top side, so it will be finding net attraction force in downward direction. So because of this net attraction force, it will try to compress down the molecule which is just below this. Okay, as it will try to compress it down, so that particular molecule will give some resistive force and it will not allow this molecule to go down. Because of this molecule has to stay over here. So that is the situation with all the molecules which are at the surface. So all these molecules have to stay at the surface because they cannot move down. Whenever they are trying to move down, they are facing some repelling force from the bottom because they are trying to cross their border. Okay, so there is some attraction forces are up to certain intermolecular distance. If you further try to, if molecules further try to come closer to each other, then the forces, the nature of forces will change from attractive to repulsive. Okay, so as these molecules will have tendency to cross the border, so these will actually, the nature of the forces will change from attractive to repulsive, and because of which these molecules have to stay here only. Okay, so as these molecules are staying over here, constantly they are trying to compress the molecules beneath them, and these molecules are constantly subjecting them to certain amount of force. Okay, so that is the reason that they are constantly this free surface of water which is consisting of this type of molecules, this free surface is in tension. Okay, so I can say all these molecules are nothing but in unhappy state. They don't want to stay at the surface, but forcefully they have to stay at the surface because some molecules at least have to stay at the surface. So that is the reason we get nothing but a free surface in case of liquids. Okay, and this particular free surface is always in tension because molecules are not in balanced state. Okay, molecules always have the tendency to come inside and they are being forced to stay at the surface, so that's why surface is always in tension. Okay, so that is the reason, if you, so this is a big container. In this big container, though molecules are trying to come towards the core, but they cannot and they are forming a free surface. Now in place of this, if you take a very small volume of fluid, so if you take very small volume of fluid, so every molecule will have tendency to come to close, come towards the center. So as all molecules will have tendency to come closer towards the core, it will form nothing but a sphere. Is this point clear? What is the reason for formation of sphere? In case of bulk, molecular forces are not that high so that this can overcome the potential energy. This can displace the molecule from this point to this point in order to make it a proper curve. Okay. But in case of small volume, they are having sufficient forces so that they can form a surface in the form of a curve. Okay. So here gravitational force is large, here gravitational force is small, so that is the reason surface tension force is dominating and molecules are behaving like a spherical seal in order to minimize the area. Okay. So why they minimize area? Because the molecules which are staying at the surface, these are having tendency to move towards the core. Okay. So that is the reason that our liquids form the surface, and whenever the volume of liquids is small such that gravitational field is not much dominant, then these forms nothing but a spherical seal. Okay. So whenever this free surface is in tension, what I told that this free surface is always in tension. So if I take any cross section normal to this, so of course normal to this will be having certain w amount of width. Okay, so if I take any fluid element at the free surface which is having width w, that is subjected to constant amount of force which is parallel to this surface, and this particular force is actually represented in terms of some coefficient sigma s. Okay, here sigma s is called as coefficient of surface tension, or simply it is called as surface tension. Okay. To understand this this concept with more clarity, let us consider one example. Say I have a U-shaped structure of wires. So these are some rods which are arranged in this U shape, and all these rods are nothing but fixed in space. Okay, and among these rods we have another rod over here, and this particular rod is nothing but movable. This rod is movable. Okay. Now what I have done in this particular arrangement, in between these rods, I have created a soap bubble. Okay. So what I have done, I have created a soap bubble surface over there. Of course, it will not be spherical shape, so I should not call it bubble, but I should call it as soap film. Okay. So what I have done, I have created in between these surfaces some film over here. Okay. So this film is having some surface area A. Okay. Now we know that this rod will be having certain thickness. So say this is the thickness of the rod. Whenever we have created the soap film, so one interface of the film will be attached to top portion of the rod, and one surface of the film will be attached to bottom portion of the film. Is this one clear? So whenever we are having a soap film, it will be having two free surfaces. One free surface connected to top portion of the rod and one free surface connected to bottom portion of the rod. Okay, is this one clear? So now you might have observed this. If I have this surface of surface area A, and say this rod is very lightweight, such that its weight is almost negligible, that it cannot induce any effect of gravity over here. Okay, and also we are considering that this is placed in such a way so that this is over here frictionless, or having very less friction at the ends. What will be happening? If you create a soap film, and if you are having rod something like this, what will be happening? Because of the surface tension, characteristic of the fluid surface is that it should minimize its surface area. Okay, in order to minimize its surface area, this fluid free surface will try to pull the rod in the left direction. Is this point clear? Whatever I am trying to say? Because it is, this free surface is having some area A, but inherent property of the surface tension is that it does not, the liquid molecules does not want to stay at the water surface. If liquid molecules does not want to stay at the water surface, these will try to minimize the surface area. Okay, and with an attempt to minimize the surface area, the molecules will try to push the rod towards the left side so that surface area is actually decreased. Because molecules don't want to stay in unhappy state. Whenever they are at the free surface, they are in unhappy state. Okay, so molecules don't want to stay at unhappy state. Okay, so that is the reason that these molecules will try to pull the rod back. Now, if I want to maintain this rod at this location only, I have to apply some force in opposite direction to maintain the rod. So, say F is the amount of force which I am applying in opposite direction in order to maintain the rod at this particular location. Okay, so what I can say is that now if I consider the rod, so this is my rod, and if I draw the free body diagram, then F amount of force we have applied on the rod in order to keep it fixed at a given location, and this rod is connecting two liquid interfaces, one from the top and one from the bottom. Okay, so these two liquid interfaces will supply surface tension force. Sigma S is the surface tension coefficient from top as well as from the bottom as well as, or I can represent it more in a more better way over here. So this is the cross section of the rod. At this cross section of the rod, so say if I take any section over here, so this is the cross section of the rod. At this cross section, F amount of force is subjected in rightward direction, and from top free surface as well as from bottom free surface, we are finding that sigma S coefficient of surface tension is actually acting in inward side. Okay, now let me consider that B is the width of this cavity, so I can say B is the width of the rod. Okay, so if B is the width of the rod, then I can say that this surface tension coefficient is acting at which point? It is acting at this line. Okay, surface tension coefficient is acting nothing but at this particular line. So what I can do, when I do the force balance, at present I have represented this sigma S as nothing but coefficient of surface tension, but this coefficient of surface tension I have to now convert into a force. When I will be converting it into the force, I can write sigma S is its magnitude, and it is acting at two interfaces. One is at this point, other is at this point, and B is width of each interface. So sigma S into 2B will be equal to F. Is this one clear? So from here, what I will get that sigma S is nothing but equal to F divided by 2B. What is 2B over here? 2B is nothing but the periphery of the interface at which surface tension is acting. Okay, so this is periphery of the surface, periphery of the free surface, or in other sense I can say it is nothing but a length parameter. Okay, so from here I can say that surface tension force is nothing but force per unit, surface tension coefficient is nothing but force per unit length, because of which the unit for this can be written as Newton per meter. In SI system, unit of surface tension will be Newton per meter. Okay, so one definition of surface tension coefficient which I have got over here is nothing but, so sigma S into 2B is surface tension force, but sole quantity sigma S is nothing but coefficient of surface tension. So coefficient of surface tension is defined as surface tension force per unit the line at which this force is actually acting. Okay, now this is one representation. Other representation can also be in terms of area and surface energy. So in terms of area and surface energy, how you can do, you can consider that, say this was at area A, okay. Now you have applied force F in such a way so that it is displacing through distance delta x, okay. Our surface is now displacing through some area delta x. So now what will be the work done over here? Of course we know that work done is nothing but F into delta x. So delta x is our displacement and F is the force, and this F is nothing but balanced by the surface tension coefficient, because this force F is acting at this point only because of the surface tension. So whenever we are displacing this rod to the right through distance delta x, we are overcoming nothing but the force which is acting because of the surface tension, okay. So I can write this W as nothing but F delta x times, and F I can replace with sigma times 2b into delta x. So delta x is this displacement and b is width in other direction, okay. So b into delta x will be the area of planar portion through which surface area of the free surface has now increased from one side.
Sir, if we are balancing out the surface tension using the force F, how can the rod be displaced?
So over here what we are considering, delta x, we are considering the infinitely small deformation. So that is the reason, in order to meet this deformation, we have to supply some force which is F plus dF, and dF is infinitesimally small, so just I am balancing with the static force of the surface tension, okay. So what I am trying to say that I am displacing the rod, but I am displacing the rod in quasi-equilibrium. So you might have heard this term in the subject of thermodynamics, okay. So we are trying to displace the rod in a quasi-equilibrium fashion. So if any excess force dF we have to supply, its magnitude is actually very small, okay. So now this is the b distance and this is delta x. So b into delta x is this added area in one direction, and we have free surface from both the sides, from top as well as bottom, because we have maintained a soak film in between the rods. So that is the reason I am having this 2b delta x is nothing but total increase in surface area when we have displaced the rod, okay. So I will be getting sigma s times dA as nothing but my change in area, okay. So from here if you see, sigma s is becoming nothing but W by dA. So what is W? W is work or energy, okay, and dA is incremental increase in area of the surface. So in this sense, unit of W will be joule, okay, and unit of area is meter square. So unit of surface tension can also be represented as joule per meter square, and this particular definition tells us that surface tension is nothing but, surface tension coefficient is nothing but the amount of work or energy required to increase the surface area of a liquid surface by some amount, okay. So amount of energy which we are investing in increasing the surface area of the liquid, that is also something which is given in the form of coefficient of surface tension. Why we need to invest the energy? We need to invest the energy because whenever we are creating a free surface, we are bringing the liquid from core to the free surface, okay. And as I told you in the previous discussion that the liquid, that the surf molecule which is at the center or at the core, that is in the happy state, and molecule which is at the free surface, that is in unhappy state. So I am trying to pull this molecule. If I have to increase surface area, what I have to do? I have to displace this plate further down. When I will be displacing the plate further down, some of the molecule from the core has to enter to the free surface. So whenever we are trying to bring the molecule from their stable condition to the unstable situation, from happy state to unhappy state, we have to invest some amount of energy to keep these molecules always in tension. Okay, so we have to invest some energy. So whatever the amount of energy we are investing in order to increase the inner area, in order to move the molecules from core to the free surface, that is something per unit area can be given in terms of coefficient of surface tension. Okay, so now we will stop, and what are the different implications of surface tension, that we will study in the next.